In the last video, we talked about standing wave ratios, SWR, or voltage standing wave ratios, and the half wavelength cycle. So we're going to test that. And what I said was that the incident waves and the reflected waves, they combine and result in impedance differences that vary with distance along the line and return to its original position every half wavelength. Okay, so in this case here, we have a cable here. I'm going to leave it open, and we're going to send an RF signal down here. When it sees it open, or it could be a short, it's going to send all the voltage back, so the reflected voltage will come back. Now, if the line happens to be one wavelength long, then our impedance is going to be 0. So we don't want to cut our cable to make it the length of the frequency. So I'm going to change the frequency. I'm going to lower the frequency until I get to 0 impedance, and then I'm going to raise that frequency back up. And when it hits 0 again, that should be half a wavelength. Okay. Now, SWR, if you have an SWR of 2 to 1, that means that the peak voltage here is going to be 2 times that of the minimum voltage over here. So this wavelength has a SWR of 2 to 1. Over here, this is 0, so it doesn't matter what this is up here, this voltage. Our SWR is going to be infinity. So what we're going to do is we're going to write down the frequency, the resistance, and the impedance, and the SWR. And we're going to start at this point, and then we're going to see when we wind back up to 0 again, 0 impedance, and then we're going to plot it on a Smith chart and see if it actually comes back to the original 0 at a half wavelength. Okay, so I got the cable set up here. Turn this on, and I'm going to bring this impedance down. Can you see that? Bring this impedance down to 0. Oh. Okay, so and you can see that it's the SWR is high. So I'm going to put that at, I'm going to start at, there we go. I'm going to start at 14.5. Okay. Now, what I'm going to do though is I'm going to add a resistor here, 150 ohm resistor, and it should give us a SWR of 3 to 1. We'll see what happens. All right. Well, we have an SWR of, I guess I'd say it was 2.4. And we have a resistance of 121. And our reactance is going to be 0. Now, I don't know if it's capacitive or inductive reactance. We're going to just assume it's going to be capacitive reactance. So now I'm going to go up to 15. And that's going to be 104 and 19, impedance of 19. And then I'm going to go up to 15.5. I'll write these down. 15.5, 68, and let's see, 40. I'll call that 40. And then I'm going to go up to 16 and 16. I'll go to 40, 46, and 33. And then I'm going to go up to 16.5 megahertz. Oop. And that's going to be, I'd say that 32 and 25. And then I'm going to go to 17 megahertz. And I'm going to call that 25 and 15. And then I'm going to go to 17.5. And I'm going to call that, I'll call that 20 and 2. And then I'm going to go up to 18. And that should be at 0. So that's 18 gets me to 0. And 16 and 0. Okay. So now I'm going to rewrite all these figures down, and I'm going to normalize them by dividing by 50 because I have a 50 ohm cable, and then we're going to plot it on a Smith chart, see what we have. I'll turn the video off for now. All right, I normalized everything. Now I forgot to write down the SWR, but I went back and looked, and it looked like it was all pretty close to 2.4. So I normalized it. This is a 50 ohm cable, so I divided everything by 50. So I'm going to start plotting the resistance and the impedance on the Smith chart. So the first one is a 2.4 ohms. So we go over that's 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. I'd say right there, and 0 impedance. Okay. Now we're going to assume this is capacitance, and so I'm going to go with 104 and 19. So so 104, it's normalized is 2.08, so it's about 2, let's call that 2, and 19, so and 0.38, and 0.3 is here, and 0.38 should be along this line somewhere, and it should be right in there somewhere. And then we're going to go with 1.3 and 8. So we got 1.3 is right here, and 8 is down here. 0.8, okay. Try that. And then we're going to go to 0.96 and 0.66. 0.96, that's almost 1. And then 0.66 is over in here somewhere. Hard to tell, but maybe, see, that's 0.6. Call it right in there somewhere. And then I'll go 0.5 and 0.3. So 0.5 is over here, and 3 is right over here. So that's there. And then I'm going to go to 0.4 and 0.04. So 0.4 is there, and 0.04 is going to be, I think, right there. And I'm going to go to 0.34 and 0. So 0.34 should be something like that. All right. So we're back to 0 again. This, from this point to this point, is 1/2 wavelength on the Smith chart. Okay. So you got 180 degrees here, and so from here to here is 180 degrees, 1/2 wavelength. So we have a sort of a semicircle there, and if we take a compass here, let's just see what happens. Close, okay. And we draw a circle through here, and that's our half wavelength circle. And now I probably messed up on the on my meter here a little bit, but you can see that the points line up fairly good here, and so that's 1/2 wavelength. So anywhere along this point, this here is the SWR is going to be the same. You know, it varied here a little bit with us, but from this point, and this is what the first number here is 2.42, and that was our SWR when we started off, and it winds up over on this side here. So I think it's working out all right. So that's our half wavelength cycle, and when you plot it on the Smith chart, it comes out pretty good. I could probably you know, use a better meter, and you know, now the trouble with this resistance is some resistors are frequency dependent. This happens to be a metal film resistor, It might have some, there's metal wound around and coiled around there, and it might have some inductance in there. And even carbon resistors can have some capacitance or change with frequency. So that could be part of the problem here. But anyway, that's the half wavelength cycle on a Smith chart, and halfway around the circle is 1/2 wavelength. So thank you.